So welcome back to Math 365, partial differential equations. And last time we talked about what some people call the linear transport model, what some people call the continuity equation. There are three fundamental equations to PDE, the wave equation, heat equation, and Laplace equation. And you might call, even some people do call the transport equation sort of like the fourth fundamental PDE. And that's why we spent some time deriving it and getting into it. But if you remember the model that we used last time, there were certain assumptions we had to make to reduce the spatial dimensions down to one, namely, we're really, even though we say we're working with an artery, we're really working with sort of like a straight line with just, two endpoints. And we really had this function u of t and x that was like the mass density of the oxygen concentration of the point. So it was mass over length, and we kind of got away with that by assuming constant density on each slice. But I mean, this is supposed to be PDE, so why not actually go for it and kind of more legitimately look at this model as something with three space dimensions and one time dimension. So perhaps I will always put a hat over vector quantities, but since x did represent a single variable last time, now I'll use x hat for general three-dimensional coordinates. And everything I do today could be generalized to like n spatial dimensions. I just prefer to keep a specific model in mind. The same model from last time, namely oxygen concentration in the blood pool. And I'll try to set things up a little bit carefully, because when you pass to multiple dimensions, it's like passing from single variable calculus to vector calculus. Like a lot. It's not just like trivialities of adding more notation. There are really new geometric things to consider. Okay, so for that reason, I'll kind of set things up from the beginning. So let us now designate the letter R to denote some cylindrical region, perhaps. Inside the artery. So like last time we went from A to B, where A could be arbitrary. So now let's really take a slice in free space. If you're following along in the text, then this region is assumed to be something called C1. I'm gonna say something a little bit different. I'm gonna say assume that it is piecewise C1, or say assume that the boundary. I'll explain. Is piecewise C1. And what does this mean? Well, so the boundary. This is my notation for boundary. So the boundary consists of these three pieces, right? It consists of the outer cylinder and then these two disk ends, right? So it's really like 1, 2, 3 pieces kind of glued together along this singular seam. This is also the notation for partial derivative, but that's absolutely not what it's referring to in this case. It's referring to the boundary overall. Okay. And this is very common notation.
Thank you.
We are quite productive, and it's not so bad. It's not so bad of an abuse of notation. And anyway, so I want to explain to you what does it mean to be C1 and then what does it mean to be piecewise C1. And this is a little bit of perhaps vector calculus review. But the way you should think of it is that dr is C1. So C1 referring to a function is C1 and its partial derivatives exist at r continuous. So how can a surface be C1? So boundary of R is C1 if is locally the graph of C1 function, and I'll even explain that in a little bit more detail. So what does it mean to be locally the graph of a C1 function? So this isn't, this is not a course on differential geometry, so I'm not going to be spending lots and lots of time on this, but I want to give you a clear idea of what I'm talking about. And so, for example, you look at the circle. So this is an example of something that is locally a C1. It's the boundary of the disk, and it's locally C1. And what I mean is that if you pick any point, like maybe you pick this point, then I can find an interval on one of the coordinate axes, in this case the x-axis, with the property that if I look at the corresponding interval of the circle, I can write this as the graph of a function. And so we know that implicitly the circle has this equation, x squared plus y squared equals r squared. And then you should know that if you want to put the graph of this point, then you can write y as a function of x. So you can write y equals square root of r squared minus x squared. But this formula is not the graph. The graph of this is not a circle, right? The graph of this is like this upper part of the circle without these 2 points. And so if you picked a different point, you picked a point down here, then you would need the negative of this to show that there's an interval around this point that's also the graph of the function. If you pick this point, then that's really not covered by either thing because there's no interval around here to make this, section the graph of a function. But it doesn't matter; it doesn't have to be the x-axis. You can also go to the y-axis and write x as a function of y. So you could use something like so even though you might have to use 4 different equations and then piece them together, that's fine. Locally, there's going to be some coordinate plane where you can express the, a portion of the graph surrounding the point, the neighborhood of the boundary surrounding the point, as the graph of that function. And the function that it's a graph of needs to have its partial derivatives existing and be continuous. And then that's called C1, and that's what's called an C1 boundary.
How closely do the C1 functions actually a provisional curve?
Well, yeah, right. So the graph of this has to be the boundary. Must be.
But you write a graph that you could write a function that only locally mirrors the boundary later.
So there has to be some neighborhood around the point under which the graph of the function is certain that neighborhood gives you this.
Outward effect.
What happens outward doesn't really matter. And you are piecewise C1 if you can take your boundary and partition it into pieces, that each one of them being C1. Okay. So any questions or comments on that definition? I'm really only saying this so that I can state theorems that will actually be true. Um, we won't necessarily be, using these definitions in a lot of depth at the present moment. Maybe we will a little bit later in the course, but I don't want to refer to things without explaining them. Yeah.
Is there a particular reason we are stating that it is piecewise C1 instead of just C1?
Well, yeah, because if you read the text, they say just C1, which is fine, but then the model that we're trying to explain is not C1. So I don't want to have a theory that doesn't even cover the example that we're talking about, but it doesn't really make a difference because we're only going to be using the Stokes theorem, integration, and things like that. And all that works on piecewise C1 regions. Like when you go into vector calculus, all the statements, fundamental theorem of calculus works for piecewise differential, piecewise continuous function. Stokes theorem works for piecewise C1. Okay, and so as before, we now have some function whose domain any fixed time t is this region, this cylindrical region. And this is once again the like the mass density, the concentration of oxygen in the bloodstream.
The actual equation be like the wave equation.
It'll still be the transport equation, so I'll write it.
Oh, yeah, but like the actual artery.
No, I don't.
Your artery. Or the actual equation of blood flow.
But the density of the blood isn't changing. It's just that the position of the blood is.
So like the heart beating would certainly change your velocity, would certainly determine your velocity function. But it's I guess I'd ask you for a derivation, in the same way that I presented the derivation that explains this model. Yeah.
When you say transport, is that equivalent to advection in the set?
So advection describes the transportation of particles in a fluid medium, and the transport equation is a particular model of advection. So I guess they're not exactly the same. Okay, and so once again, units have to be mass over volume. Just like last time they were mass over length, because length of the region here played the role of volume in that case, but now this time it's actually properly volume.
Can we take the dimensions beyond this 30?
Yeah, just add more variables. So I invite you to do that.
You heard the conceptualize, yeah.
It's not even that hard to conceptualize. You just if you have any physical model that uses more than 3 variables. Doesn't, or just any PDE that involves more independent variables. They can be different in spatial, like temperature, pressure, and so on. Okay. So what I'll do now is we introduce, like before, this quantity Q, and last time, so it's the flux density, and so it is again this time, except you have to interpret it a little bit differently now, because now this is a vector quantity. So it's a vector quantity characterized by the following equation. So the domain of this is, the entire artery, right? And now you can take a piecewise C1 region R, which you can think of as like a small cylindrical slice, but it could be any region with piecewise C1 boundary in here. And you can ask yourself the question about flux. You can say, given some region, I'm looking at the rate that the mass exits that region through the boundary. And that rate is going to be given by the following. So you want to take the multidimensional integral over R. So the 3D integral over R of this flux vector at the time t, and then take the dot product with what we call the outward unit normal. And then just take the volume integral. So, excuse me, over the boundary. And so this is going to be.
So like if the fluid were not flowing directly, directly through the surface, that angle is correct. Exactly correct.
Yeah, so the fluid can kind of flow however it likes, but mass can only exit if it's going straight out, right? So like you say, if the fluid is kind of flowing out a little bit or like seeping out, you're really only interested in the component that's going straight out, because that vector splits up as normal component and tangential component, and the concentration that's flowing tangentially will not exit the region. So you're looking at the amount of mass exiting the region, so you want to take the dot product of this vector. So this almost behaves in a similar way that the gradient of a function behaves in that, like its dot product kind of gives you a partial derivative.
Wait, so the second vector is just the vector normal surface.
Yeah, this vector nu is called the surface normal, and it's a unit vector that's orthogonal to the what we call the tangent plane of the surface. Right? And so if you remember, maybe this is familiar from your vector calculus class. If you fix some point on the boundary, then this surface perhaps is parameterized by u and v. So you can look at vector du, vector dv along the surface.
If I remember,
You draw a sphere for it. And then and so then the normal vector you can get by really looking at cross product, and then just divide from the length in order to make this unit. Because you don't want to mess up the integral by having some extra scaling. And so for this region, on the pieces, on the singular seams, there won't be a normal vector, but on each C1 piece, you'll be able to write down that parameterization because the thing is the graph of something, right? And you'll be able to take the cross product and normalize it, and it will look as I've indicated. You kind of see that how here you've got one direction and then the straight other direction and cross products. And I mean, U and V have to have like a right hand orientation, otherwise it might not be outward. But, yeah. Was there a question? This is new. It's a group that are new. It's the outward pointing one.
Is that capital new or little?
That's a lowercase new.
The vector we use to describe a plane. Right?
You can characterize a plane in terms of its normal. It's great. Yeah, and so we can now kind of go through this derivation almost exactly like we did before, and it won't take too long, and it'll give us the same thing. So let's see what we've got. So let's write down our conservation equation. So I want to say that the rate of change of the mass. So first of all, like, what's the mass? In analogy to last time, the mass in some region R is going to be just this integral over R. Of the mass density, right? So mass density has units of mass over volume. The integral then gives you units of volume which cancel out, and you're left with actual mass. And so the rate of change of this, you can calculate it in different ways. You could, of course, take the derivative of the integral sign, or you can use this physical conservation law, which is basically going to relate the change in mass to this physical quantity. So if this is the mass that's exiting, then it's going to change the mass. You know, it's going to make the derivative negative, right? So this is the amount of mass, like the positive number representing the mass that's exiting, which then makes the derivative decrease. So you want a negative sign. Sometimes I'll do xt and sometimes I'll do tx. I apologize for that.
Why did we also integrate along the wall of the vessel?
Well, you don't have to in this case, but just for completeness of the theory, like you need to have a region with a boundary in order to do calculus. Yeah. And in this case, everything works out because like you can kind of imagine the flow, right? Like you're going this way, or maybe you're taking some twists and turns or whatever. But and I know the actual arteries has some thickness to it. It's not like, so there's no like blood flow in the artery, so the model isn't perfect. But if you imagine like what's happening sort of close to the artery, and just extending the function up, you can see there's definitely no blood going out. So the flow is tangential. So I think that in other words, the flux physically ought to be tangent, you know, at that point. Yeah. The flux can't have a normal component because there is no change in concentration like going that way, which zeroes this out. So that's another advertisement for why you like to more. So now that we've got this going here, that's right. You should use the divergence theorem, which is like our multi-dimensional analog of the fundamental theorem of calculus. And what that tells us is that dot product of this vector with the normal derivative should be what? Like the divergence? vector q
over the surface.
over the surface integral. Actually, I kind of did something wrong. I should have said eval. I should have said ds for the surface. And now this is the three-dimensional volume integral. So this is the divergence of q. It's a scalar quantity. So
Not simpler.
what?
That is not a lot simpler.
Well, anyway, it's just an equation relating these two quantities. And so what I've got now is I've got dm dt equals the negative divergence. And there's a convention in PDE, so yes, Q has 4 variables, but this divergence only applies to the spatial variables. So when I do divergence, gradient, Laplacian of a quantity that has spatial and time variables, I'm only referring to the spatial variables. Which makes perfect sense because all of this is at a fixed time t. And then you're calculating all these intervals over the region. And so dm dt you can also replace integrating under the integral sign to give you what partial of u with respect to t. And so now you put it together and you end up with what? 0 is equal to integral over r of u sub t and then plus the divergence of q.
Minus the version Q.
No. And then bring it to the other side. And so this is kind of like the analog of our first transport equation, right? And in a similar way that I showed that if you take a quantity, if you integrate from A to B, and if that quantity is continuous, and if you can choose A and B to be arbitrary, then if that interval is 0 for every A and B, then the integrand must be 0. In fact, the same thing is true here too. If this integrand were non-zero at any point, it would be either positive or negative. Being continuous, there would now be a region around that point where the integrand is always positive or always negative. Choose R to be contained within that region, integrate over it, and this value would not be 0. So once again, so long as these partial derivatives are continuous, and so long as this holds for every R, if the integral is 0, then it must also be true. You should see most of those. And so in the linear model, you make this extra equation that flux density should be u times v, right? V I didn't bring up yet, but the same thing as before. So at a particular fixed time t, v of x is your velocity vector. And so in multiple spatial dimensions, you have to actually use a vector instead of a scalar with a sign. In one dimensional, the sign is kind of like telling you the direction. In multiple dimensions, you do take a vector quantity. which is good because Q has to be vector valued. Remember, U is a scalar. And so now my first in-class exercise for you is to remember our vector calculus study. Can you calculate for me a formula for the divergence of U times V, where V is a vector quantity, U is a scalar quantity? What's the product rule say about that? I'll give you a minute and then I'll do it. Okay, after you having given you some time to work it out, I'll explain sort of in words the calculation I do to show this. Divergence is what? It's a sum of all the partial derivatives in the different spatial directions. So this is just partial with respect to x, u times v, plus partial with respect to y, u times v, plus partial with respect to z, u times v. So focus on any one of those terms, and you use the usual product rule. And so you get like u sub x times v plus u times v sub x. And similarly for the other three. So what you end up with, so what you end up with is basically for the three of the terms, that's Vx, Vy, Vz, all multiplied by u. That's u divergence V. And then the other terms are ux, v, uy, v, and uz, v added together, which is now, I can write as gradient v dot product. No, the gradient of a function.
Similar.
Be clear. And divergence is not defined on functions, divergence is defined on vectors. But the divergence of like vector v, v1, v2, v2, that's going to be right. So the divergence should be sum of all the partials.
So when you say gradient u dot z, that's the same thing as saying what
U sub x times v plus u sub y times v plus u sub v. Well, I say time. Yeah.
Yeah, so this is ux times v1, well, times v1, because it's greater than u dot product of v plus v1.
You could write u did the gradient v dot of u.
What is the rule of the triangle effect?
So well, to do one question at a time. I mean, you can't exactly do that because u is not a vector; it's a scalar. But you are, taking this quantity and just multiplying it through by u, and those should give you the 6 terms from the chain rule, or excuse me, the product rule from vector vectors. And
What is the rule of the triangle?
not one.
Okay, now I know I can do that. The triangle alone, as with the dot with the vector, is the vector. Right.
Oh, no, the divergence is the sum. The partials.
Which is not close to it.
Okay. Well, yeah, I think we'll move to the vector calculus discussion to office hours. And so, what I do want to do, yeah, let's just finish up the calculations. So, what we've got is so this divergence becomes u times the divergence of v plus gradient of u dot product of v. Equals 0. And so here's now your linear transport equation. In higher dimension. And I use it with 3 spatial variables, but it's exactly as written with more spatial variables with the appropriate meanings of divergence and gradient. So when I'm doing stuff like this, I like to understand not just how the special case generalizes, but also how the general case specializes. So can I apply this formula to my previous model and make it kind of work out? Like if you go back to this, right? So what's the analog of this in the one-dimensional case? So in one dimension, when you just have the lump, your boundary is just the 2 endpoints. So maybe you let me write it like that. And an integral over a boundary is just, an integral over 2 points is just evaluation of those points. We're integrating flux vector times normal vector, outward normal. And outwards, in this case, the line comes with a natural orientation going this way. So I think the outward normal to the line is like that vector. And the outward normal here is this vector. So that's our nu in this case. The real line is a one-dimensional vector space. So you can think of that as a vector. And so Q had this interpretation where this was supposed to equal the amount of mass exiting through the boundary at that time. And so how can we do that? So if we take vector Q. So what is Q as a vector quantity? I think Q as a vector quantity points this way. Sort of telling us the you know, the mass going in that direction from the orientation. And in the 1D case, what did we say? We just said that dn over dt. Well, we said that the amount exiting was what? We said it was like the stuff going in, which is Q of A T, minus the stuff going out, Q of B. And so this isn't exactly what you get if you just integrate over the 2 points, which would be like adding them together, right? But if you dot product with the normal vector, you get sort of +1 here and -1 there. So this minus sign going to not work out for me somehow. I feel like the analog of this integral is like integrating over 2 dots with Q being dot product with a negative thing here, you know, giving you a negative number here, and this dot product being equal to 1. So I feel like this should naturally give you Q of BT minus Q AT. Except it's like does that work out okay? Because now this, by the fundamental theorem of calculus, is nothing but integral from A to B of dq dx. Yeah, just like before. And then, whereas for here, the analog of fundamental theorem of calculus was divergence of Q. Well, what's the one-dimensional divergence of Q? This is dq. So apologize for taking time on that, but I think it's actually kind of nice to take care of every single minus sign and, you know, make sure that when we're talking in high dimensions, we know that actually how to do it in one dimension. Okay, fine. So we have linear conservation equation, and we have another physical simplification we can put in. So I'll give you this physics definition, which says that a fluid is incompressible if divergence of velocity is equal to 0, and in this case, I'm specifically talking about our linear transport model. So fluid subject to this model is incompressible. The divergence of the velocity field is 0, and in that case, this equation reduces to u sub t plus gradient of u of p. And the physical interpretation of incompressible is not that the fluid is incompressible, unfortunately. The physical interpretation of this is that if you apply pressure that doesn't come from heat or cooling, so if you heat the fluid or cool it down, it could expand or compress and therefore change the value of u because use the density. The fluid occupies a smaller space, the density would have to increase to conserve mass. So if you are compressing this fluid in a way that doesn't change the heat, so like isothermal pressure, same heat, same level of heat, pressure, then the concentration of the mass will not change as you're going along a characteristic line. So it doesn't even say that the fluid can't be compressed. It says that if you compress the fluid in a way that's not related to heat, then along the characteristic lines, that's where the mass is guaranteed to not change. So it's not even uniformly saying that the concentration won't change as you expand or contract it. And so why is it true that the density is constant on the characteristic lines? That's actually an alternate definition. You could say if the Lagrangian derivative du dt equals 0. So these two conditions are completely equivalent as long as you're talking about a fluid subject to this linear transport equation. And the reason why. The reason why, so you've seen the method of characteristics. Last time in the higher dimensional case, you want to solve the same thing as before, dx dt equals velocity with x plugged in, and here in this case, x is the vector quantity of spatial variable. But then you solve this with, with Picard's theorem, with the ODE theorem. And then you plug it back into the equation just like before. So just like before, you have this term. Like you write down the general equation, u sub t plus gradient u dot v plus w equals 0, and then our case w is equal to u times divergence of v. But in general, w could be any term that depends on x, t, and u. This term will be du dt, and you can check that. Because I'll remind you that what it literally is the total derivative of u with x sub t plugged in. And just going through the chain rule, you see you get u sub t times derivative of t, which is equal to 1. And then you get, ux times derivative of x plus the dy times the time derivative of y. Use these, the dots to represent a time derivative. It's uz times time derivative of z. That's the chain rule, isn't it? And so this is u sub t plus gradient of u plot it with dxdt. You concentrate it and you plot it. Okay, so you get this equation that says u dt plus w twiddle equals 0, where w twiddle is simply w with x of t plugged in for x, with your characteristic plugged in for x. Just like last time. And then I was telling you these two conditions are equivalent, and now you can see that they're equivalent because, on the one hand, if du dt is equal to 0, then w twiddle is equal to 0. But w twiddle is this quantity with x of t plugged into u. Nothing changes with divergence. So if this is 0 with x of t plugged into u, then divergence of u is equal to 0. Conversely, if divergence of v is equal to 0, then w twiddle is equal to 0, and therefore this derivative is equal to 0. And therefore, incompressible means that u constant on characteristic. So remember, u is the mass density. So for incompressible fluids, the density has no choice but to remain constant on those characteristic curves.
What's the definition of characteristic curve?
Characteristic curve is a solution to the equation dx dt equals v. So a characteristic curve is this function, t gets sent to x of t, and it solves dx dt equals v. I just wrote this. So I think I need to close off fast right now, but if I can open, next time with some picture or something, or like in this model, you take some characteristic curve that might look like this. It's just you've got your velocity vector field, right? And you're searching for a path whose tangent vector is equal to that velocity vector. Those are the characteristics. So it's just a curve. When you take the tangent vector along the curve, you get the. Yes, I mean there's one for each initial condition. And incompressible is saying that the mass density doesn't change as you're flowing along. And so examples of incompressible fluids that work with this model, certainly blood in our model, and also water. So thank you everybody for your time and attention. There's an example I can show you with this. I'll start out the class with that next time, and then we'll continue on to some other parts in chapter 1 of Logan. Maybe talk about the